Hello, my name is Felipe Gonçalves, and I'm a postdoc here in the University of Bonn, and this will be the videos for the class about the Collatz Conjecture. So this will be an advanced topics in analysis class for the master program in the University of Bonn, the master program mathematics, of course, about the Collatz Conjecture, also called the 3x plus 1 problem. More information about the class you can find in my website. So these lectures will consist in a series of papers. So I will read these papers about the Collatz conjectures and the techniques and methods involved in some of the progress towards the conjecture. And I will read those papers and I will make notes, which will be available in my website, and I will present these in these lectures, and we will work it out some of the together some of the methods and techniques in these papers. And the spirit of the class is that you listen to the talks and read the papers and try to have ideas for yourself. Maybe you can find some nice observation, and even maybe you can solve the problem or some partial progress, like some nice partial progress on it. That's the purpose of the talks, like just to understand what are the techniques and problems and issues involving the 3x plus 1 problem. There is a nice survey from 1985 of Jeffrey Lagarius. So both these papers are from Jeffrey Lagarius. Okay, and there is also one nice bibliographical review. This is from 2010, where basically he lists all the relevant, basically almost all the papers ever done up to 2010 about the 3x plus 1 problem, and also talks a little bit about like one paragraph or so about each one of these papers. And this material here, the last one you can find on arXiv actually. The first one is a paper. Okay, so without further ado, let's start the lecture of today. So, in any case, if you have any questions about how the class will proceed and etc., you can send me an email, or you can look in my website. Just a quick note about my website. My website is without the S here on my name. My name is Gonçalves, but my website is without the S in the end. So today's paper will be about a paper of Terras from 1976, and it's called a stopping time problem on the positive integers. And this is this will be the paper of today. But before we start with the paper of today, maybe you are wondering, what is this 3x plus 1 problem about? So let me try to explain here. So the 3x plus 1 problem is about the asymptotic behavior or assertive map. Okay, the 3x plus 1 map, also called a Collatz map. So from now on, C will be the map from the integers to the integers, positive integers, sorry. So Z plus would be just 1, 2, 3, 4, 5, etc. The positive integers, defined the following way. So this defines the map completely, but another way of writing the map is the following. C of n equals n over 2 if n is even, and 3n plus 1 if n is odd. Well, if n is odd and then 3n plus 1 is even, so if you apply the map again, it would just divide this by 2. So we can do that already. So we divide this by 2. And you can see that these two maps agree exactly. But these are just two different definitions of the same map. So the game here is you take an integer and you start iterating it under this map. So you take C of n, and you take C of n, and C of C of n, and so on. And you look for of this orbit of this map. So the iterates of this map. And you ask the question, what happens with the iterates of this map? So let's try some examples here. So the first one would be, let's say, start with the number 1. If you start with the number 1, 1 is odd, you multiply by 3, add 1, you get 4, you divide by 2, you get 2. So this goes to 2. But 2 is even, then this goes back to 1 and gets into a loop. So let's try the second number, let's say 3. If you start with the number 3, but 3 is odd, then you get to 5. 5 is odd, then you get to 8. And then since 8 is the power of 2, then you get to 4, 2, 1, and then you go back to 2. So you get in this loop again. So we tested 1, 2, 3, 4, 5, there's 6, 7, and 9 and 10 up to 10 to test. So let's test those. Let's test also 4. Well, 4 is already here, so let's test 6. Well, 6 is even, it goes to 3, and from 3 on we know what happens. Okay, it also eventually gets to 1, and then, eventually gets to 2, and then it cycles back and gets into the cycle again. If you try with 7, 7 would be a pretty long chain, and I guess we contain 10 as well. So 7 is odd, so it goes to 11. And that goes to 17. And 17 goes to 52, then you divide by 2, it goes to 26, which goes to 13, which goes to 20, which goes to 10, and then 5. And then from 5 on, you know what happens? So from 5 on, we know that it eventually gets to 2, and then to 1, and then it cycles back to 1. Okay, so we did all the numbers up to 10, because 10 is here as well. Okay, so it seems that all the numbers up to 10, they actually go back to 1. I was just checking if indeed I was recording the class. Okay, so every number goes back to 1. So the conjecture is, so now I can erase this part here. Okay, let me erase this. So the conjecture is the 3x, the Collatz conjecture. There are a bunch of controversy about who stated first the problem and how old is the problem actually. So there are some people that prefer to call it the 3x plus 1 problem because of that. I'm calling it the Collatz conjecture anyway, but this can be discussed, I guess. So the Collatz conjecture is that for every integer greater or equal to 2, there is some k such that ck of n equals 1. So that's the Collatz conjecture. Every integer eventually goes back to 1. And one of the difficulties to show this conjecture is that the Collatz map, it's kind of a random, but it also has some structure at the same time. So it seems that it lies on the interface of something which is completely random and something which has a lot of structure. So it's hard to grasp what's going on here and really why this thing has to go back to 1 for every integer. Okay? So the paper today will be a paper of Terras, and and the main question here in this paper, in my point of view, is that he asks, well, suppose we cannot prove the Collatz conjecture, can we say at least a density statement? So can we say that for a certain density of the integers, a certain number, proportion of the integers actually goes back to 1? Can we say something like that? And that was I think the main motivation for this paper. And actually Terras is get some nice results. And and you will see why. It all comes from a simple observation, very nice simple observation, and then everything falls into place. So so we'll have to make some definitions. So the first definition, I will define this function which we will call x, for the moment, which is nothing but just n mod 2, and I'm using the percent notation here for mod 2. Just basically 0 if it's even, and 1 if n is odd. And then you realize that c of n is nothing but 3 to the power x of n times n plus x of n, everything divided by 2. It's a simple thing to notice. And so this function x actually is defined in a way so that to make the map just a simple expression and something you can iterate easily. Okay. So let me define another function which is sigma of n, with the minimum between the k is greater or equal to 1, such that ck of n is less than n. Okay? So this is called the stopping time. Of n. So it's the first iterate, the first k, the first element of the orbit of n that actually is less than n. Okay? And so we define also there's another function which is the minimum of the k is greater or equal to 1, such that ck of n is actually 1. So it's the first guy that actually hits 1. Okay, so now you realize that the Collatz conjecture, let me call this like this, the Collatz conjecture is equivalent to the statement that, and this function here, I can say that, so this is the stopping time, and this function here is called the total stopping time of n. Okay, so I'm using the nomenclature of Laguerre's 1985 paper. Okay, so we'll try to follow most of the notation initiated here. Okay. Well, since I'm making a lecture about a bunch of papers, all these papers have their own particular notations. I have to establish a consistent notation for this class. So sometimes I use some notations from some paper and the other, and from some other papers. Okay, so if you actually read Terras' paper, you won't see sigma. Sigma there is another letter. Okay. So the Collatz conjecture now, so coming back to this point, the Collatz conjecture now is the statement that sigma the total stopping time is finite for all n greater or equal than 2. It's kind of obvious. And also almost trivial is that actually this is equivalent to saying that sigma of n, the stopping time, is finite for all n greater or equal than 2. And why is that the case? Well, suppose that sigma of n is finite for n from 2 to a certain capital N. Okay? Well, clearly this implication is obvious, because if you iterate and eventually gets to 1, then definitely it will be less than n at some point. So this implies this. Now I'm showing this, that this implies this. Okay, so suppose that sigma of n is finite for n up to 2, from 2 to capital N. So that means that for any such n, there is k1 such that c of k1 of n is less than n. Okay. Well, but c of k1 of n is an integer also between 2 and n. So if ck1 of n is 2, then you're done, because when you iterate next, if ck of n is 2, then you're done, because when you iterate next, you will get to 1, and 1 would be less than in any of these numbers. If it's not, then it's a number between 2 and n, and you can iterate one more time. So there will be some k2 such that c of k2 of n is less than c of k1 of n, k2 greater than k1, of course, less than 2, so greater than k1, such that this happens. And then you can continue this, and since you're forming a decreasing sequence, eventually this will have to be hit 2 or be below 2 or be 1. So that will imply, after several iterations, that there will be some KL, such that C of KL of n is actually 1, which is the same to say that sigma infinity of n, the total stopping time, is finite. Okay? So Terras here will focus on the study of the stopping time, not the total stopping time. The total stopping time is something harder to handle, but the stopping time is something better, and that will be the focus of Terras' paper. Let me erase the board. So the main theorem of this class, the main two results of this class are the following. So Theorem One, the following limit exists for all k greater than or equal than 1. So when I'm saying, so this thing here is the set of all natural numbers n less or equal than m, such that sigma n, the stopping time, is less or equal than k. So I'm taking this set and I'm computing the density of it, which is set divided by m and goes to infinity. So I'm saying that the density, this set has a proper density, which I defined by fk. Note that in Terras' paper, his fk is actually 1 minus our fk. Okay, but I prefer to define this way. So fk, so this limit exists, and fk converges to 1 as k goes to infinity. Okay, that is, so actually, so not only f converges to 1, well, f is always less than 1, or less or equal than 1, so this is always positive, but this is less or equal than 2 to the minus eta k. So that's why it converges to 1, where eta is some very small quantity, which is just 1 minus h of gamma, where gamma is log of 3 in base 2 inverse, and h is the entropy function in base 2, which is minus x log of x minus 1 minus x log of 1 minus x in base 2. Okay. So gamma here is something like 0.63 ... Will actually be important to know exactly, more or less what gamma is later on. Okay, so in the case, so fk converges to 1. So an almost direct consequence of this result is theorem 2, which is that, let me define pi star of m as the number of n's less or equal than m, such that the stopping time is finite. Then converges to 1 as m goes to infinity. So this is just a statement that almost all integers have finite stopping time. Okay? And if you, with a bit more of work, you can do that as an exercise, or you can look in Lagaria's 1985 survey. You can actually show that 1 minus pi star of m over m, of course this is always positive because pi star of m divided by m is always less or equal than 1. This is actually less or equal than some constant c divided by m to eta. Okay, so that's why it converges to 1. You can even make a quantitative statement about it. So I only show Collatz 2. With a bit more work, you can show this as an exercise, or you can look in Lagaria's survey. Okay, and the proof of Collatz 2, actually you can do it very easily. So that the proof of Collatz 2 is actually very simple. Well, if we do pi star of m divided by m, well, this is always less or equal than 1, but this is always greater or equal than, I simply do 1 over m cardinality of m less or equal than m, such that sigma of n is less or equal than k, for any k I choose, because if it's less or equal than k, then it's definitely finite. Therefore, here is a larger number than here. But then if you take limits on both sides, if you take the limit inf in m here, and you take the limit inf in m here on both sides, the limit inf here on the right hand side actually converges. This is the statement of the theorem. This is fk. So from this, you conclude that 1 is greater or equal than the lim inf of pi star of m over M, which is greater or equal than Fk. But Fk is converting to 1 when k goes to infinity, therefore the limit inf equals 1. Well, but the limit sub has to be less or equal than 1 as well because of this identity. So it implies that limit inf equals limit sub equals 1, therefore the limit exists and it converges. And it is 1. Okay, so that finishes the proof. So let k go to infinity and you can finish the proof. Okay. So corollary 2 is almost all integers have finite stopping time. And that's the main message of Terras' paper, which is corollary 2. Almost all integers have finite stopping time. Okay. So for instance, if you want to test if the Collatz conjecture is true up to a certain capital N, one thing you could do is just a test to compute the total stopping time for each n up to this capital N. But that you don't need, because by this argument here, you only need to make sure that the stopping time is finite up to n, because that would imply the total stopping time is finite. And that will make the amount of computations you have to do smaller. So that will improve a bit your algorithm if you actually try to do this in a computer. Okay, let me erase the board. So what Terras realized is that this probability here, this density Fk, can actually be computed in a very explicit and nice way. And this comes from an observation, basically. So first, let me... so now what we do is a series of lemmas to show Theorem One. And then in the final part, we make some comments about cycles. Okay, so the first lemma is the following. Let xk of n be simply x of ck of n, which is basically just you asking for the parity of the k iterate of n. Okay, so in particular, x will be my x naught here. Okay. So then, ck of n is nothing but just lambda k of n and ok of n, where so lambda k is this quantity here. Lambda k of n is just 3 to s of n divided by 2 to the k, where s of n is just the summation of these x's, so x naught of n plus xk minus 1 of n, and whole k, let me drop the n here and just write it like this, lambda k over 2, and then x naught lambda 1 minus 1 plus x1 lambda 2 minus 1 plus x k minus 1 lambda k minus 1. Okay. So how can we prove this lemma? Well, the proof is straightforward. It's just a proof by induction that those kind of easy to do proofs by induction. Let me just do the first few steps and you see that it will work. Well, if k is 1, then C of n is nothing but, well, the formula that I wrote before is just 3 to x naught divided by 2 times n plus x naught divided by 2. And that matches exactly with the proposed formula. So this is okay. Let's see C2 of n. Well, C2 of n is basically just 3 to the power x of C of n times C of n divided here by 2 plus x of C of n divided by 2. Well, this is exactly 3 to x1 divided by 2. C of n is the previous one, which is 3 to x naught divided by 2 n plus x naught divided by 2 plus x1 divided by 2. So what you get is 3 to s1, oh sorry, s of 1. Yes, 3 to x of oh, I should put here as index in s. Sorry, this should be s. Okay. Okay. So this is s2 because it would be x1 plus x naught divided by 2 squared times n plus, and then we will have these two guys here. But let me put 3 to s2 divided by 2 squared and then an extra 1/2 here, which that guy here is exactly, this guy here is exactly lambda 2. So this guy here is exactly lambda 2. So what will we have here? Well, we should have just 3 to x1 over 2 times x naught over 2. So we have the over 2 here. So what I'm missing is just a 2 divided by 3 to x1. 2 to x naught, sorry. And that will multiply x naught plus, and the x1 I'm missing everything basically. So this would be 2 squared divided by 3 to x naught plus x1 times x1. So this is exactly lambda 1 inverse, and this here is exactly lambda 2 inverse. So the formula works, and then you can finalize the proof by induction. Okay, it's easy to do argument by induction. Okay, so you have to remember these functions now, because I will be using those functions over and over. The function lambda and the function whole, function s, and the function and the x. Okay. Let me erase the board. So now is where the key insight of Terras comes into play. So let me define these functions here, ek of n, which is nothing but just x naught of n up to xk minus 1 of n. Okay, so basically you're just getting the first k iterates starting, so n, c of n, etc., and ck minus 1 and n, and taking that mod 2. So this would be just a vector of zeros and ones of length k. Okay? So the lemma is the following, that ek of n equals ek of m if and only if n is congruent to m mod 2 to the k. Okay? In particular, ek is 2 to the k periodic, and ek from the set 1 up to 2 to the k, so you get all the residues. All the residues mod 2k. Well, this will map into a series of vectors. This is a bijection. Okay, so the consequences are almost trivial because, well, if this is true, then obviously the thing is 2k periodic. But, and in here, what happens is that for all these numbers, all the vectors ek of n, for any n in this set, will have to be different by the first part of the lemma. Therefore, there is at least 2 to the k different vectors in the range of this map. But here we have exactly 2 to the k vectors. So ek is merely just listing all the vectors in this, all the vectors of size k with only zeros and ones. Okay. So this seems something very nice, very wonderful, but it's actually just a very simple observation. And again, Terras paper is a very nice paper, which is just basically a series of easy, not easy, but simple observations that leads you to a very nice result. So how do you prove that? Well, the proof is basically just establishing the claim. Claim for every I from 1 to k, we have this identity. Okay? In particular, if this is true, okay, so suppose the claim is true for a moment. So if the claim is true, that means that the parity, so this is the orbit of n plus r to the 2 to the k times 2 to the k, and this here is this part only is the orbit of n, and you know that the difference between term-wise, entry-wise of these two vectors in these orbits is just a multiple of 2. Well, because lambda I by the definition is just a power of 3 divided by 2 to the k. So lambda I is at most dividing by 2 to the I, which I is less or equal than k. So this is just an even integer, so up to k. So that means that ek equals of n plus r 2 to the k equals ek of n. Okay? Yeah, exactly. So that means that they are equal. So So that is the if part. If they are congruent mod 2k, then they have to be equal. Okay? But then it comes the question, if they are equal, then you realize that the iterates, if they are equal, mod 2k, that means that they differ only by a power of 2 to the k. But then you look for them for this definition here, and then you see, and then you can apply. So you see that the functions lambda k and ho k only depend on these vectors. Therefore, since the vectors are equal, the parity vectors are equal, ek of this guy equals ek of this other guy, that means that ck of n, so this implies that, so this is the first part, and if ek of m equals ek of n, then that implies that lambda k of n and ho k of n equals, say this vector here, equals lambda k of m ho k of m, because they only depend on the parity vector. Okay, so sorry, I, for every I from 1 to 0 up to k minus 1, even up to k, and well, if that is true, then you realize that ci of m is nothing but lambda I of m, but lambda I of m equals lambda I of n times m plus ho I of n. Okay. Yes. But and ci of n equals lambda I of n plus ho I of n. So that implies that their difference, ci of m minus so I want to show that m is congruent to n mod 2k. That's what I want to show. Oh no, that's kind of obvious. Yeah, because if this is true, then well, the first vector has to be equal to the second one. Oh no, not okay. Okay, let's continue. That's not so obvious. Okay, let's continue. So now you have this. Yeah, that's the calculation, the right calculation. Because I want to show that they are equal mod 2k. So that would be equal to lambda I of n m minus n. Okay, so if I put for k here, and this is up to k, sorry. Maybe let me use the full force here. This is up to k. So lambda k of n m minus n. Well, but that means that, well, this is an integer, and lambda k is just an integer divided by 2 to the k. Okay? It's just 3 to some power divided by 2 to the k. So that implies that 2 to the k divides m minus n. Okay. Okay. So again, so the claim. So if I prove the claim, I finish the lemma. And the claim is very easy to show just by argument of induction. So let me show the first steps, for instance. So what is C? So let me show the claim. So showing the claim. So how can I show the claim? Well, let's just do the first few ones. So suppose I have C plus R 2 to the k. So what is this guy? Well, yes, so what is this guy? Well, this is simply lambda, this is simply 3 to x of n plus r2 to the k divided by 2 and then n plus, and this is just x of n plus r2 to the k divided by 2. But again, this is just computing the parity of the vector, which is equal to the parity of n, so I can erase this. And this is just xn. The same here, I can erase this part. And this is just xn. And that was exactly the formula we claim here. This is just c of n plus, then you have this term times this, and this exactly is lambda 1 n. Okay, so it works for c of n. Let me erase the board. Let me try C2 of n. And for C2 of n, we will use the formula. This is lambda 2 of n and then plus O2 of n. So, and then what happens with C2 of n plus R2 to the k? Well, again, they use the formula. But then you realize what lambda 2 of n plus r2 to the k. Well, I just showed that n and n plus r to the k have the same parity. And what happens with c? With c of n plus r to the k and c of n have the same parity because their difference is an even number because k is greater or equal to 1 by assumption. So I know, so from this, I realize that E1 of n equals E1 of n plus R2 to the k. Therefore, when I do this thing, I get this, because the functions lambda and whole only depend on E1, the vector E1, and they are the same for n as for n plus r2 to the k. So therefore I get the same thing. So then I get here exactly C2 of n plus r2 to the k lambda 2 of n. And so on. So you finish by induction. When I say finish by induction, I'm not really doing any induction argument here. I'm just merely showing you how I'm merely showing you that's going to work. I mean, it's not an actual proof, but it's just giving you a sketch how you're going to do that. Okay. So once you have this very nice observation that the parity vector, this ek, is actually a 2k periodic function, you get into a very nice position here. So let me make some other definitions. So before I define, I want to define another stopping time function, which we call the coefficient stopping time, and it is based on a simple observation. So suppose I have, observation. Suppose I have ck of n less than n from some k. Well, by our formula, that means that lambda k of n times n plus whole k of n is less than n. But that can only happen, since whole k is a positive quantity, that can only happen if lambda k is less than 1. So that implies that lambda k of n is less than 1. So if I define omega of n equals the minimum of the k is greater or equal than 1, such that lambda k of n is less than 1, I conclude that omega of n is less or equal to sigma of n. Because whenever sigma of n actually is finite and is k, I get that this k also is less than 1. That means that my omega could be less or equal than sigma. So that inequality happens. And one thing to realize is the following, that the set of the integers, such that omega, so the set of integers greater or equal than 1, such that omega equals k is 2k periodic. And well, why is that the case? Well, it's a very simple observation. Because these functions, lambda I, they are 2i periodic. Why? Because lambda I only depends on the vector ei, but the vectors ei are 2i periodic. Therefore, the function lambda I is 2i periodic. So, so this thing here is exactly the same statement that lambda 1 of n up to lambda k minus 1 of n, they are all greater than 1, greater or equal than 1, but lambda k of n is less than 1. That's the exact statement. But all these functions here are 2k periodic because they are 2i periodic for some I less or equal than k, therefore also 2k periodic. So all these functions here are 2k periodic. So this set is 2k periodic. Okay, and they can't be equal 1. Recall that lambda is basically just a power of 3 divided by a power of 2. So they cannot ever be 1 unless these two powers are 0, which is never the case. So this is actually greater than 1. Okay, so this set is 2k periodic. Therefore, this set has a density. Okay, so let me call this the density, which is the probability. That has a density, and it's merely just 1 over 2 to the k, so of the n is less or equal than 2k, such that omega n equals k. Okay? Because a set which is periodic has a density, and the density is basically, you just count the number of members of the set up to the period, which is to the decay. Okay? I'm going to erase this board. So far so good. We're almost getting there. Now we can go to lemma 5. Which is the following. If omega of n equals k, okay, so n has, I didn't say what the name of this function. So this function is called the coefficient stopping time. Okay. So the coefficient stopping time is always less or equal than the stopping time, sigma n. So if n has coefficient stopping time equals k, then sigma of n plus r2 to the k, the stopping time will be k for r large. Greater or equal than 1 and large. Okay. So we know that the set omega n equals k is 2k periodic. So if omega n equals k, that means that all its all the representatives of n mod 2k will have coefficient stopping time k. So all these numbers here have omega equals k. And this is saying that, this is saying that sigma of n will be k for r large. So it will agree with omega in the tail of the set. Okay? So in particular, as a consequence of this, the set omega in particular, there is, what is it? Well, let me make this comment later. Okay, let me first show the dilemma, and then I can make this comment later. Okay, so this is really almost trivial. And here's the reason. Well, the functions lambda k and whole k are 2k periodic. Okay, that we know. So, ck of n plus r2 to the k will be equal just to lambda k of n plus r2 to the k plus whole k of n. So r is the one which is moving here, which is changing. All n and the n and k are fixed. And also ci of n plus r2 to the k will be lambda I of n plus r2 to the k plus whole I of n. Why? Because these functions here are 2i periodic, therefore 2k periodic if I from 1 to k minus 1. Okay, so the condition that omega n equals k is the condition that all these numbers here are greater than 1. Therefore, this quantity here is greater than. So all these numbers are greater than 1. Therefore, this quantity here is always greater than n plus r2 to the k. Okay. Well, that's the statement that sigma of n plus r to the k is greater or equal than omega of n plus r to the k. Okay, that we already know. But also when r goes to infinity, so this guy here is less than 1, and these two are fixed. So when you do this, what you get is lambda k of n, which is less than 1. And whole k of n divided by n plus r2 to the k. So when r goes to infinity, this quantity here decreases when r goes to infinity. This whole quantity here decreases to lambda k of n, which is less than 1. Okay, so for some r, sufficiently large, this thing will be less than 1. And since all the previous iterates were greater than n plus r to the k, so then you conclude that sigma of n plus r to the k will be equal k if r large. And I finish the proof. So it's almost trivial. Okay. So one observation from this is that, well, if you take the set, so on a nice observation from this is that if you take the set omega equals k, okay, if you take the set omega equals k, we know that, suppose I take the set sigma equals k, so stopping time equals k. Well, we know if it's equal to k, then omega is less or equal than k, so that's contained in the set omega less or equal than k. Well, but the set omega less or equal than k is just the union of j equals 1 to k of the set omega equals to j. Okay? However, in each of these sets, you can split in residue classes modulo 2j or 2k if you wish. So, so if you take this intersection, okay, well, we know that if I intersect, this set can be split in a union of, let's say of a from 1 to 2 to the j, okay, of w equals j intersection sigma equals k intersection n congruent to a mod 2j. Okay, so by the previous lemma, if this thing is non-empty, that is, there is some n congruent to a mod 2j such that omega of this n equals j, and also sigma of this n equals k. Once I go further in the integers, for larger and large integers, positive integers, by the lemma, sigma will have to transform to j. But this is impossible because I'm intersecting with the set equals to k. So it means that all those sets here, so these are finite. All these sets here are finite. Therefore, this set here is finite. Okay? For every j less than k. So this is for j less than k and greater or equal than 1. So we just concluded the following, which we can express very nicely in words. The set concluded the following. So we conclude that the set omega equals k and the set sigma equals k differ finitely. Okay? So these two sets, they differ only finitely. Okay. Well, here we just show that sigma of k is contained in omega equals k. Of course, maybe I should put this. That the set omega equals k is definitely contained in the set sigma. So this thing shows that sigma, the set sigma equals k, is basically contained in here, and if it's not, there are only finitely many differences. Okay, but then the set omega equals k. If omega equals k, then sigma is greater or equal than k. But then eventually, by the other lemma, sigma will become k in this set. So a similar argument as this one will show that. So basically, you have to do a similar argument for this one to show that for a finitely. Okay. So lemma 5 really implies that if you want to measure density of this set, then you basically just have to measure the density of this set. So let's write that in the lemma. Yeah. Let's write that in the lemma. Again, so this argument shows that sigma equals k is basically contained in omega equals k, and the difference is only finite. So if you take the set omega equals k, so if sigma equals k, and I remove the set omega equals k, this is finite. Okay? So I have to make the other remove. I have to also show that the set omega equals k, if I remove the set sigma equals k, this is also finite. But it will be a similar argument. Okay, so they differ finitely. So lemma. So what we just showed in words is the following: that the limit of m to infinity of 1 over m cardinality of n less or equal to m, such that sigma of n equals k equals the probability of omega equals k, the way I defined before, and we know that this is basically just 1 over 2 to the k cardinality of m equals 1 or m less or equal to 2 to the k, such that omega of n equals k. Okay. So now we are ready to, almost ready to start the proof. So lemma 6 is proven just by the comments we did. But then what I want to make another definition, and then we can start the proof. So let me get a vector in 0, 1 to the k, and we call this vector inflating. If so if I go from so inflating, if all its partial sums of size of length I is greater than I gamma for every I from 1 to k. Okay, where gamma here, again, gamma is the constant we define, is log of 3 base 2 inverse. Okay? So then note now the following, that what is the statement that omega of n is greater than k? Well, that's exactly the statement that lambda 1 of n up to lambda k of n is greater. So the statement that omega of n is greater than k is exactly the statement that lambda 1 of n up to lambda k of n, they are all greater than k. Than 1, sorry. Well, all these functions here are 2k periodic. Therefore, this set here has a density. And that is the same as the density of all these guys being greater than 1, which will be exactly 1 over 2 to the k, cardinality of n less or equal than 2 to the k, such that lambda 1 of n up to lambda k of n, they are all greater than 1. So again, recall that lambda can never be 1, so is it less than 1 or greater than 1? Okay, so this is the density of the set. But what is that? Okay, so this guy here is depends only on the vector ek. Okay, so it depends only on x0 up to xk minus 1, these functions here. Okay, so this thing, what it means is, well, lambda I, so suppose I is less or equal than k, so lambda I of n being greater than 1 is the same as 3 to the sum of the various si of n, which would be x0 plus xi minus 1 divided by 2 to the I. This is greater than 1. So if you take log on both sides, log in base 2, you conclude that x0 plus xi minus 1 has to be bigger than I gamma. Okay, but again, what is this? This is the so if I call epsilon equals the vector ek, then this is the same as to say that epsilon is inflating. Okay, but recall that ek is a bijection between the integers less or equal than 2k and all the vectors of length k with only zeros and ones. So we conclude by the fact that ek is a bijection, so it's merely just enumerating all the vectors with only zeros and ones and of length k, we conclude that the probability of omega greater than k is just 1 over 2 to the k, cardinality of epsilon in 0, 1 to the k, epsilon inflating. Okay? So with this observation, we can prove our main result. Okay? So how the proof goes. Now it's a very, it's a simple sequence of steps. So, what is Fk? Well, Fk by definition is the limit if it exists, but it will exist because we actually already showed that. And this limit exists because all these quantities can be written as so this quantity can be written as a sum of quantities, all having a limit. So all these guys have limits, so we know what this is. This is exactly just sum from j equals 1 to m, 1 over 2 to the j, cardinality of the n's less or equal to 2 to the j, such that omega of n equals j. Well, because the set omega n equals j is 2j periodic, okay? But since it is 2j periodic, it's also 2k periodic. Oh, this is k, sorry. This is k here, and this is k there, sorry. The set, if something is 2j periodic is also 2k periodic, so therefore I can simply change, this is still j, but simply change this things here, and then again you have that this is just 1 over 2 to the k cardinality of the n less or equal to 2 to the k, and omega n less or equal to k. Okay, so now we know what is 1 minus fk. Well, 1 minus fk, well, it has to be the probability when omega is greater than k, which we computed that. We also can do just 1 minus this, which we know what it is. Okay, and we know what this is. This is exactly this probability here, as it had to be. Okay, and this is exactly just 1 over 2 to the k, the epsilons in 0, 1, such that epsilon is inflating. Okay, but now notice if epsilon is inflating, then we have several inequalities, but 2 of them are k minus 2 greater than k minus 1 gamma, and which equals k gamma minus gamma, but k gamma yes, I'll just that. So, no, this is for later. So what I want to do now is bound this from above. So here I have a bunch of inequalities in the definition, which is this one. But let me drop all these inequalities. This require 1, which is epsilon naught plus epsilon k minus 1 greater than I gamma. Okay? Well, that means that this is exactly saying that the number of ones in epsilon is greater than I gamma. So, and this can easily be counted because you have a vector with a certain number, let's say I, of this is supposed to be the very last one, which is k. Sorry. So I'm only using the very last inequality here. So I'm dropping all the conditions here to something, so getting effectively a larger set. Okay, so bounded is quantity by above. So what's the number of ones in epsilon? Well, the number of ones in epsilon, if you have a vector of zeros and ones, and you fix the number of ones equal to j, let's say, how many of those vectors can you do? we're going to do exactly K choose J. Yes. We can do exactly K choose J. Okay, and now I'm going to use an inequality for this kind of sums. It comes from effectively bounding the rate of convergence of the central limit theorem. And you can find the reference of the inequality I'm going to use in Lagaria's 1985 paper. The inequality I'm going to use is the following. That this sum here, this part here, is less or equal than this. And then is only true if gamma is greater or equal than a half, for all gamma greater or equal than a half, and which is our case because gamma, let me recall you, gamma is like 0.63 ... So since gamma is greater than a half, I can apply this inequality where h is the entropy function. So I get exactly 2 to the minus eta k, where eta is 1 minus h of gamma. Okay? So that finishes the proof. Okay? And just as a final remark, I want to talk just for some minutes about cycles. So the proof is very cool. I mean, just a series of very simple steps, but it gets you to a very nice place. So as, before I talk about cycles, as you can wonder, there is a conjecture, which is the coefficient stopping time conjecture, if you want, that the stopping time is always equal to omega. And that has also been verified up to very large numbers, and it seems to be true, but we can't prove it. And also, I don't know how to, if this is true, how to then use that to prove the Collatz conjecture. It would still be very hard if you know this to prove the Collatz conjecture. So the final result of this class is Theorem 7, which is the following. Let mk be equal to the max of I gamma divided by 2, 1 minus 3 to the power I gamma divided by 2 to the I for I from 1 to k. Then the set that omega is less or equal than k and n greater than m, so let's see, n greater than m k and omega n less or equal than k. This set is contained in the set that omega n equals sigma n. Okay. So this is in direction of the conjecture, saying that, well, if you know that a coefficient stopping time is less or equal than k, then there is an effective m, such that if n is larger than this m, then actually the two sets are equal. Okay, so this is again a very simple proof. Well, imagine that omega n equals I, which is less equal to k. Okay. Then if you put epsilon as the vector e, let's say ek of let's say ei of n, then you know that epsilon is almost inflating. But the last one is actually less than I gamma. Well, because it's exactly the same computation we did before. I mean, this is exactly equal to the statement that lambda L of n is greater than 1, and this one is exactly to the statement that lambda I of n is less than 1. Okay, then you realize something. You realize that epsilon naught plus to epsilon I minus 2, that's greater than I minus 2 gamma, which is I minus 1 gamma, which is I gamma minus gamma. So that's just this inequality here. But I gamma is greater than this. So then you conclude that epsilon I minus 1 is actually less than gamma. Oh yes, there is a minus gamma here. Yeah, so you can cancel epsilon naught up to epsilon I minus 2 with these ones, and you get this inequality. So that implies that epsilon I minus 1 is 0. Okay. And then you go back to this identity here, this inequality here, and you move gamma to the left-hand side. So you get that this is greater than I gamma, which is, so I add gamma in all the parts here, and I get, so you conclude that I gamma is actually equal to epsilon up to I minus 2, but then you can add epsilon I minus 1, because this is 0. Okay. Okay, and then what happens? Well, we have Hoi of n. And Hoi of n is lambda I over 2, and then epsilon naught lambda 1 minus 1 plus epsilon I minus 2 lambda I minus 1 plus epsilon I minus 1 lambda I minus 1. Well, lambda I is less than 1. All these other guys are greater than 1, so these are less than 1 because they are inverted. And this guy here is 0. So we conclude that all this thing is less than epsilon naught plus epsilon I minus 2 over 2, which is equal to I gamma, the integer part, over 2. So this symbol here that I'm using is just the integer part of I gamma. Okay? Then we are almost there. So now what we do is, well, suppose, so if n is greater than mk, well, which is greater or equal than I gamma integer part divided by 2, 1 minus 3, 2i gamma over 2 to the I. Well, that is greater than by what we did, whole I over n. And then you have 1 minus this, but this is exactly equal to lambda I of n. Yeah, because of this identity here. So then you conclude that n is greater than lambda I of n times n plus whole I of n, which is ci of n. So that implies that sigma of n is less or equal than I. Okay, but omega of n was I, so that implies the I equals omega n, which is always less or equal than sigma n, which is less or equal than I. So that implies that omega n equals sigma n. Okay, so indeed, if n is greater than mk and omega n is less or equal than k, then omega n equals sigma n. And what nice, so this finishes the proof. And why is this nice? Because of the following observation. So assume we check that sigma of n is finite for n less or equal than m k. Okay? So, yeah. So suppose that happens. Suppose you have a cycle. So assume. So suppose we do that. Then my claim is, then there is no cycle of C of length less or equal than k. Now suppose not. And n naught is the minimal element. Of a cycle of length less or equal, let's say length equals I, less or equal than k. Okay, so, and I'm assuming the cycle is not the trivial one, of course. I'm assuming that it's not the 1-2 cycle. So therefore, I know that sigma of n naught is infinity, because it never gets to be less than n naught, because it always goes in the cycle, and since this is a minimal element in the cycle, it never gets to something smaller than n naught. So that's infinity. Okay? Well, but that implies by this that n has to be greater than mk. Okay? But if you have a cycle of length I, that means that after I iterations in n naught, which is lambda I of n naught plus whole I of n naught, I get to be n naught again. But that means that lambda I of n naught, if this identity is true, has to be less than 1, which means that omega of n naught is less or equal to 9. Okay? So omega of n naught is less or equal than I, which in particular is less or equal than k. So omega of n naught is less or equal than k, and n is greater than mk. Okay? But then by the previous theorem, omega of n, but by theorem 7, omega of n naught should be equal to sigma of n naught, which is infinity. It's an absurd. So we get to a contradiction, and so there is no cycle of length k. And this is a very nice result, so you can test numerically how large if there is, how large other cycles have to be. Because if the Collatz conjecture is not true, either you find some n that iterates and goes to infinity, or it gets trapped in a cycle which is not the trivial one, 1, 2, 1, 2. So, and this gives bounds for how far away these cycles can be. Okay, so, and we will do a numerical. One of these videos will be a numerical about numerical part of the problem, where we will explore this thing and other things as well. And I hope you enjoyed this video, and see you in the next class.